So in the time response analysis, the syllabus which is given is the time response analysis of standard test signals, and the time response of first order systems, and characteristic equation of feedback control system, transient response of second order system, time domain specifications, steady state response and its error constants. So these are the contents having the time response analysis. Before going to the time response analysis, we have to know a few basics related to this time response analysis. So as we know that the transfer function of a system is nothing but Laplace transform of output by Laplace transform of input. So this is the input represented with R of t, and this is the output represented with C of t. So this is LTI system, linear time invariant system, and the Laplace transform of this input R of t is nothing but here R of s. The Laplace transform of output is nothing but C of s. So by the definition, the transfer function can be defined as Laplace transform of output by Laplace transform of input at zero initial conditions. At zero initial conditions. Initial conditions are 0. So this is nothing but here C of s by R of s. So this is our transfer function. So let the input R of s, is equal to 1. So what is this one now? The transfer function will become C of s by R of s. So here R of s can be 1, then that will be C of s only. So that means if the input Laplace transform of input is 1, then the transfer function is nothing but its response, Laplace transform of its response only. So whenever the Laplace transform of input is 1, then the transfer function is nothing but its C of s only. So generally, if the input is Laplace, if the input is impulse signal, let me say delta of t, then the Laplace transform of its impulse signal, is nothing but 1. So here the Laplace transform of input is equal to 1. So therefore I can assume that this is the impulse signal, and the response when you are applying impulse signal is called impulse response. Then we can call it as impulse response. So here the transfer function can also called as the impulse response of the system. Impulse response of the system. So like this, to enter into the time domain specific time domain analysis, we need to know few basic functions related to the Laplace transform. So let us see here. So this is the input x of t and the output x of s. The Laplace transform of input x of s is, let me take unit impulse signal. This is delta of t. The Laplace transform of the input is 1. If the input is step signal u of t, then Laplace transform of the step signal is 1 by s. If the input is ramp signal or acceleration signal represented with R of t, which is nothing but t into u of t, then the Laplace transform is 1 by s square. So similarly, if the input is Tn into u of t, then its Laplace transform is n factorial by s power of n plus 1. if e power of minus at into u of t, then its Laplace transform is 1 by s plus a. Similarly, Tn into e power of minus at into u of t, then this can be n factorial divided by s plus a whole power of n plus 1. And for trigonometric functions, sin omega t into u of t, sin omega t into u of t, and its Laplace transform is omega by s square plus omega square. For example, it is cos omega t u of t, then this one will be s by s square plus omega square. If e power of minus at sin omega t into u of t, then this will be omega by s plus a whole square plus omega square. So similarly, e power of minus at cos omega t u of t, e power of minus at cos omega t u of t. So for this one is s plus a divided by s plus a whole square plus omega square. So these are the few important relations when the input is r of t and its Laplace output, Laplace transform of that input is shown in this table. And similarly, Laplace transform of differentiation is s, Laplace transform of integration is 1 by s. So these are the few important Laplace transforms for various input signals that we have to remember in this time response analysis. Now coming to the time response analysis, it is nothing but the time response of the system is the output of the closed loop system as a function of time. It is denoted by c of t, and the time response can be obtained by solving the differential equations which are governing the system. So already we know that the closed loop transfer function can be written as Laplace transform of output by Laplace transform of input. In general, we will be representing this with respect to g of s by 1 plus g of s into h of s. So let me represent this with respect to m of s. Then the output in s domain is c of s, which is given by the product of this overall transfer function and input in s domain. So on taking the inverse Laplace of this output which are in s domain is nothing but our time domain output, the time domain response in time domain, which can be nothing but the inverse Laplace of this entire transfer function m of s and the input r of s. So this is the time response in time domain analysis for the given transfer function. Here the time response of a control system consisting of two parts. First one is the transient response, and second one is the steady state response. So in the transient response, it is the response of the system when the input changes from one state to another state, and here the speed of the system can be calculated. So transient response is nothing but it is the response of the system when the input changes from one state to another state, and steady state response is nothing but this is the response of the system as time t tends to infinity, as time t tends to infinity. So, in the steady state response we can calculate the errors in the output. So, errors in the output we can calculate from steady state response. So, time response, time domain analysis is nothing but inverse Laplace of transfer output C of S is nothing but in the time domain response in the time domain analysis. So, here from this equation C of t is equal to inverse Laplace of overall transfer function into input R of S, Laplace of input. So, to understand to predict the response of a system, we must know, or we must have the knowledge of input. We must have the knowledge of the input signal, so that we can we can predict the response of the system. So, in practical case, it is difficult to expect the knowledge of the input signal, which the actual input signals are available. So, generally the characteristics of actual input signals are like a sudden shock or sudden change, or a constant velocity and a constant acceleration. So, therefore, these we have to prepare few test signals which are resembling the original characteristics which are used as input signals to predict the performance of the system. So, for that we are having few common test signals, or we can call it as standard test signals. They are standard test signals. First one is step signal. Or unit step signal. Second one is ramp signal or unit ramp signal. Third one is parabolic signal or unit parabolic signal. Fourth one is impulse signal. And the fifth one is sinusoidal signal. Generally, we will consider these as a standard test signals to predict the response of the system in time domain analysis. Since these test signals are simple functions for the time, and they can be easily generated in the laboratories, the mathematical and experimental analysis of the control system using these signals can be carried out easily. So, here we will see all the test signals and what are the characteristics of all the test signals one by one. So, first one is a step signal. So, step signal can be represented like this. This is the time t and this is the input R of t. Then the step signal can be like this. This is A. Let us take this is A. Then the mathematical representation of the step signal R of t is nothing but 1 if it is a unit step signal for all t greater than or equal to 0, and which is equal to 0 for all t less than 0. So, for unit step signal, that means the value of A is equal to 1 here, or else for a normal step signal this will be A. So, generally we will be discussing, we will be representing in this section as a unit step signal. So, therefore, I am considering A as equal to 1. And similarly, ramp signal. So, second one is the ramp signal. It is very similar to the acceleration, sorry, very similar to the velocity input to the system. So here this can be taken as, this is r of t, sorry, this is t, this is t, and this is r of t input. Then the graph will be like this, as this is 1 and here it is a, and this is 2, this is 2a. So here r of t for a unit ramp signal, the expression can be given as r of t is equal to at for all t greater than or equal to 0, and this is equal to 0 for all t less than 0. This is ramp signal or a velocity signal. And third one is parabolic signal. I am considering unit parabolic signal. The graph will be like this. This is the input t and this is r of t. So this is the square of the input. So here this is 1, for example this is 0.5a, and this is 2, and this is 2 ampere, and this is 3, this is, let me take 4.5 ampere. So the unit parabolic signal or a acceleration signal, so this is similar to acceleration signal, acceleration input to the system. So this can be given as unit parabolic signal can be given as r of t is equal to a t square by 2 for all t is greater than or equal to 0, and this is equal to 0 for all t less than 0. And the last one is the impulse signal. This impulse signal is nothing but at 0 input we are having maximum output. So theoretically, like at 0 input you have to get maximum output. So this is time t and this is the impulse signal or input r of t, which is nothing but delta of t, impulse signal. And actually this is the actual impulse signal. We are having maximum or infinity output at 0 time, but practically it is not possible to measure. So we are taking like this, having certain duration like a by delta in 1 by delta. Next one is order of the system. Order of the system. Order of the system. So generally we will be describing transfer function as shown. The transfer function can be represented with Laplace transform of output by Laplace transform of input, C of s by R of s, or I can represent with b naught s power of m plus b1 s power of m minus 1 plus b2 s power of m minus 2, so on, b m minus 1 s power of 1 plus bm divided by a naught into s power of n plus a1 into s power of n minus 1 plus a2 into s power of n minus 2, so on, a n minus 1 into s plus a n. So here numerator polynomial having the power m, s power of m, s power of m minus 1, so on. And similarly we are also having denominator polynomial having the powers with s power of n and s power of n minus 1, so on. So the order of the system is given by the maximum power of s in the denominator polynomial is called the order of the system. So order of the system is nothing but here the maximum power of s in the denominator polynomial. So therefore n is the order of the system here. N is the order of the system. For example, if n is equal to 0, then the system is called a 0 order system. If n is equal to 1, then the system is called a first order system. And similarly, if n is equal to 2, then the system is called a second order of the system, so on. So here the denominator polynomial, the maximum power of the denominator polynomial representing the order of the system. Here I can write the transfer function with numerator polynomial as p of s and denominator polynomial as q of s. So therefore I am factorizing the above equations, polynomial equations, with respect to the roots of the polynomials. So I am representing like this: s plus zm divided by s plus p1, s plus p2 and s plus pn. So here z1, z2, z3 are the roots of the numerator polynomial, and p1, p2, pn are the roots of the denominator polynomial. So the roots of the numerator polynomials I am calling it as zeros. So these are nothing but here roots of the numerator polynomial, and I am calling it as poles, roots of the denominator polynomial. So roots of the numerator polynomial can be called as zeros, and roots of the denominator polynomial can be called as poles. Here the zeros and poles are the critical value of s at which the transfer function p of s attains extreme values of 0 or infinity. When s takes the value of 0, the transfer function will be 0, and when s takes the value of a pole, then the transfer function p of s will be infinite. That's why the names called 0 and pole. So that means here this is the transfer function having numerator and as well as denominator. If the roots of the numerator are zeros and roots of the denominator is called poles, that means these are the two critical values of s. When s is taking the value of 0, then the transfer function will be attaining the value of 0. If s is taking the value of a pole, then the transfer function will be attaining the value of infinity. So that's why these two are very, very important in the analysis of transfer function. Response of first order system. So this is a closed loop transfer function of a first order system. So if I write the transfer function of this is nothing but g of s by 1 plus g of s into h of s having unity feedback. So here the g of s is 1 by st and divided by 1 plus 1 by st. So this can be written as 1 by 1 plus st. So this is the transfer function of the first order system, because the maximum power, the initial value of the system, initial value of this response can be calculated as, if t is equal to 0, then the value of this time response is limit t tends to 0 c of t, which is equal to 1 minus 1, which is nothing but 0. The final value of this response is t is equal to infinity. That means limit t tends to infinity, c of t is nothing but 1 minus 0, which is equal to 1. Or we can convert this one into S domain and we can calculate this one. So like this one, limit s tends to infinity s into c of s, so which is nothing but limit s tends to infinity s by s into 1 plus st. So this one will become s by s into s, so this will become 0, limit s tends to infinity. So like that we can also do this one. And if the graph, if we draw the graph, this is time t, this is c of t, and the graph will be like this. So actual value is here unit step signal, so this will be the value of 1. So let us calculate here how this graph will be. When t is equal to 0, when t is equal to 0, then c of t will be 1 minus e power of 0, which is equal to 0. When t is equal to 1 time constant, then c of t will be 1 minus e power of minus 1, that is equal to 0.632. When t is equal to 2 time constants, c of t will be 1 minus e power of minus 2, which is equal to 0.865. Similarly, when t is equal to 3 time constants, c of t is equal to 1 minus e power of minus 3, which is equal to 0.95. Likewise, when t is equal to infinity, c of t can be written as 1 minus e power of minus infinity, which is equal to 1. So the maximum value is 1. The maximum value is 1. So here, but practically this is reaching up to here only. So this is 1t, the value is minus 0.63. This is 2t, the value is here 0.86. This is 3t, the value is here 0.98, and this is infinity, so somewhere it will be reaching to 1. And here up to 5 time constant, this is the response called transient response, and after 5 time constant this can be called as steady state response. And this is the difference between actual value and obtained value called error. So that's why in the steady state analysis we will be calculating the error in the given time response.